Hey guys, hello everyone, and welcome to Smart Question Series, your daily dose of smart problem solving. Now, we have already covered 3 videos in this particular series where we have discussed about different questions related to quantum chemistry, related to different topics, starting from your CSIR NET June 2024 exam, and we have also discussed some question from GATE 2024. So this particular video is about a particular question from phase equilibria and a concept of lever rule, which is we generally don't study when we prepare for CSIR NET or any other exam. So the idea will be to explain you about the lever rule and to understand how that question will be done. The other part of this video are there in the playlist of Smart Question series. You can click on this I button and you can access the whole playlist and watch the other videos as well. These are going to be super important because these videos are short and they can just give you idea of a particular topic and how to solve a particular question related to that. All right. Now, having said that, let's start with the question over here. So this is the question which was asked in CSIR June 2024 exam. The question says that a mixture of 0.6 moles of hexane and 0.4 moles of nitrobenzene was prepared at 300 Kelvin. Based on the phase diagram given below, this is the phase diagram given below, the number of moles of hexane in alpha phase is, okay. Now, alpha phase is hexane rich phase and beta phase is nitrobenzene rich phase, okay. So if you look upon this phase diagram, it shows you certain values. This is the temperature which we have, and over here you can see this is alpha phase, this is beta phase, and then you have different options like 0.56, 0.42, 0.38 and 0.32, and these are different values of like these lines are different values over here. Now I'll explain you first of all what exactly this is, okay, because it is super important to understand, because this type of phase diagram we generally study phase diagram of one component system or two component system, but this is also a phase diagram of two component system, but these two components, they are like these particular two of them, they are converging eutectically, okay. So that's the concept. So let's first of all understand about this topic and then we will get into detail of it. So this particular question is from a concept of two component system, okay. This is from two component system, and usually I have not seen such question, especially on this particular topic. I have never seen this type of question in CSIR NET exam in past few years. So this is something new, okay. Generally we study one component, two component system, and we generally just deal with the terms over there, or at most we discuss about the slope of the curve, melting curve, fusion curve and things related to that. But here it was a numerical type question, and that's where the concept is going to be, like we have to understand the concept. The concept which we are going to use over here is called as lever rule, okay. But before going into that, before explaining you about the lever rule, let me explain you about the diagram itself. So this is a two component system. It has two components in it. Two component means two things will be there, two chemically different things will be there, and one is hexane and the other one is nitrobenzene, okay. But the graph is plotted with respect to the temperature and x nitrobenzene. Now what is x over here? So x is nothing but it is the mole fraction of like this is the mole fraction of nitrobenzene, okay. So you are plotting, this is mole fraction of nitrobenzene, okay, written as x nitrobenzene, or in short we will write it down as, let's say, x NB. Okay, now the thing is that what you values you are seeing over here, it says that at this point the mole fraction of nitrobenzene is 0.3, here the mole fraction of nitrobenzene is 0.4, and here the mole fraction of nitrobenzene is 0.8. Now understand the system, okay. So here in this region, like outside this solid line, over here you have hexane rich phase, means you have lot of hexane over here, and over here you have lot of nitrobenzene, this is nitrobenzene rich phase. Now because both of these liquids like hexane and nitrobenzene, they are going to be like, they are going to mix with each other, although they are chemically different compounds, but still they are going to mix with each other, and that they are going to make a two component system. Okay, now over here if you see, so at any point you will have certain amount of hexane and you will have certain amount of nitrobenzene. So at this particular place, okay, because in this case you can see that the percentage of nitrobenzene or the mole fraction of nitrobenzene is increasing. So at this line, in this particular line, you have only pure hexane. Okay, sorry, yeah, pure hexane. You don't have any nitrobenzene on this line. Okay, whereas on this line you only have 100% of nitrobenzene. Okay, so on this line you have 100% or like pure nitrobenzene. Okay, so over here if you reach a little bit over here, it will be like 0.1 is the mole fraction of, so the composition is shown in mole fraction over here, how much mole fraction of nitrobenzene is increasing. So as you go in this direction, the amount of nitrobenzene is increasing more and more. So over here at this point you have 0.3 mole fraction of nitrobenzene and 0.7 mole fraction of hexane. Here 0.4 mole fraction of nitrobenzene and 0.6 mole fraction of hexane. Here 0.8 mole fraction of nitrobenzene and 0.2 mole fraction of hexane. Okay, so this is what it is. So this is a two component system shown in this way, where at this place you have 100% of hexane. Okay, 100% of hexane, or you can say that you have pure hexane, and here you have 100% of pure nitrobenzene or yeah, 100% or pure nitrobenzene, and at certain point you have certain values of or certain mole fraction of nitrobenzene. This is the diagram. Now lever rule helps you to find out like how much composition of a particular mixture, like a particular liquid you have, based upon their like mass balance. Okay, they try to balance the mass, and with respect to that it explains you. Okay, so now let's try to solve it. Let's try to do it. So as I said that this concept over here is your lever rule, and this is used in the phase diagram to determine relative amounts of two coexisting phase in system. Okay, so why this is used for? So this is used to I'll write down, it is used to determine the relative amount or relative fraction. Okay, so relative amount or fraction of two coexisting phases. To find out the fraction of alpha phase, let's say, okay, so fraction of alpha phase. Okay, so to calculate the fraction of alpha phase, let's call it as f alpha. Okay, that is denoting us as the fraction of alpha phase, and this is equals to x NB, that means the mole fraction of nitrobenzene, okay, minus the x NB, sorry, yeah, x NB means the mole fraction of nitrobenzene in beta phase. Okay, so from the total mole fraction of nitrobenzene you subtract the mole fraction in the beta phase, in the other phase, and divided by, this whole thing will be divided by the mole fraction of nitrobenzene in alpha phase and minus the mole fraction of nitrobenzene in beta phase. Okay, so this is the formula which we will use in this case. Similarly, when you have to calculate the fraction of beta phase, okay, so if you have to calculate fraction of beta phase, this is done in the same way. Let's call it as f beta, fraction of beta phase, and this will be done in this way. So this will be mole fraction of nitrobenzene in alpha phase. Okay, so NB comma alpha shows that mole fraction of nitrobenzene in alpha phase minus mole fraction of nitrobenzene, total mole fraction of nitrobenzene, divided by mole fraction of nitrobenzene in alpha phase minus mole fraction of nitrobenzene in beta phase. Okay, so this is how we calculate. So remember, when you have to calculate the mole fraction for alpha phase, you subtract the mole fraction of nitrobenzene or whatever the component is in from the beta, like you have to subtract the beta phase from the total and denominator remains same. You have to remember this formula. Okay, that is something which you have to take care of. Now I'll tell you, because I know right now you must be confused that what exactly this is x and b, or what are these things. So let's try to solve this. Okay, or let's try to understand that what exactly it says. So first of all, let's try to calculate the mole fraction of nitrobenzene. Okay, so the mole fraction of nitrobenzene, which is x and b. Okay, so the overall mole fraction of nitrobenzene, which is denoted by x and b. How you are going to calculate? You will write down the moles of nitrobenzene. So in the question you see that they have given that a mixture of 0.6 moles of hexane and 0.4 moles of nitrobenzene is given to you. So mole fraction of nitrobenzene you can simply calculate. How? You will write down the mole of nitrobenzene divided by total moles, or mole of hexane plus mole of nitrobenzene, right? That's how you calculate the mole fraction, number of moles divided by total moles. So mole fraction, number of mole of nitrobenzene is given to you as 0.4. So I'm going to write down 0.4 divided by mole, number of mole of hexane is 0.6 and plus mole of nitrobenzene is 0.4. If you solve this, you will get 0.4. So this is the value of x and b. So you got the value of x and b. Now you have to write down the values of the other things. Okay, so the mole fraction of nitrobenzene in alpha phase is here. Okay, this is the mole fraction of, let me change the color. Yeah, so this is the mole fraction of nitrobenzene in alpha phase. How? Because this one is closer to the alpha phase, and that's how it denotes, because this like this line basically this touches the alpha phase, right? That's why this is the mole fraction of nitrobenzene in alpha phase, and this value over here, this denotes the mole fraction of nitrobenzene in beta phase. Why? Because this line touches the beta phase. Okay, so the diagram has itself given you all the values. It has given you the value of x and b alpha, value of x and b beta, and you have calculated x and b. You can put and calculate. In the question they have asked you to, based on the phase diagram, the number of mole of hexane in the alpha phase. Okay, the number of mole of hexane they have asked. They have not asked about the mole fraction. They are asking about the number of moles of hexane. Okay, so for that, let's first of all calculate the like the fraction of alpha phase, because hexane is in alpha phase, right? That's in the alpha is the hexane rich phase. So let's first of all calculate the fraction, because once you calculate the fraction, it becomes easy for you to calculate the other things. I mean the mole, the mole fraction, and then you can easily calculate the other values, which is your like which is the number of moles. Okay, fine. So let's write down. So we have to calculate like using, sorry, so let's use using lever rule, fraction of hexane, basically which is alpha phase. Okay, that is calculated as f alpha, and it was given by x and b minus x and b beta, right, and divided by x and b alpha minus x and b beta. We know the value of all of them. We will put all of them. So this is 0.4 minus 0.8 divided by 0.3 minus 0.8. So it becomes 0.4 divided by 0.5 minus, okay, which gives you 0.8. So the fraction of alpha is 0.8, and the fraction of beta you do not have to you know, you do not have to put everything, or you want, you can put it, but there is another formula. If you know the fraction of one, you can calculate the fraction of other just by this formula. Okay, 1 minus fraction of other. So this is 1 minus 0.8, which is 0.2. So what we can say from here, we can simply say that there is 0.8 fraction of alpha, or you can say 80%, right? 0.8 means 80%. So there is 80% of alpha phase, okay, which is hexane, and 20% of beta phase, which is nitrobenzene. Now you must, if you are confused how I got 80%, just multiply this with 100 and you get the percentage. Okay, so if you multiply 0.8 with 100, you will get 80, and similarly 0.2 with 100, you will get 20. So you have 80% alpha phase and 20% beta phase, right? Now we have to calculate the mole fraction of hexane. Okay, so let's calculate the mole fraction of hexane. Okay, why I am doing so, I'll tell you. Okay, first of all, let's calculate. So mole fraction of hexane you can simply calculate because it is a two component system, and you already know that the mole fraction of nitrobenzene is 0.4. So you can calculate the mole fraction of hexane also, right? The mole fraction of hexane can be simply calculated. So now let's look at what the question was asking us. The question was asking that the number of moles of hexane in alpha phase. Okay, remember what they were asking. They were asking the number of moles of hexane in alpha phase. So let's calculate that. So for that, let's do all the calculation in the alpha phase. Okay, so in alpha phase, what were the values we have? So first of all, we have that mole fraction of nitrobenzene, okay, in alpha phase. What was the value of mole fraction of nitrobenzene in alpha phase? That was 0.3, right, from the diagram. Because the question asked about alpha phase, so we are only doing the things around the alpha phase. So that is 0.3, or this is x and b comma alpha. Now if you know the mole fraction of one of the component, and if the system is of two components, you can simply calculate the mole fraction of other. Okay, so mole fraction of hexane in alpha phase can be simply calculated as 1 minus x and b comma alpha, right? You have just subtracted, you can just subtract this value. So this will be 1 minus 0.3, and this will give you 0.7. Okay, so this is the mole fraction of hexane in alpha phase. Now when you have to calculate the number of moles, this is the formula where we are going to use the fraction value. Okay, the fraction value which you have calculated. So when you have to calculate the moles of hexane in alpha phase, that's what they were asking in the question, right? Moles of hexane in alpha phase. So to calculate this, what we have to do is we have to multiply the moles in alpha phase and multiply it with the mole fraction. I mean, we have to multiply the fraction over here, the fraction of hexane in alpha phase, and multiply with the mole fraction. So we have to multiply the fraction of hexane in alpha phase, okay, and we have to multiply it with the mole fraction, with the mole fraction of hexane in alpha phase. Okay, so fraction of hexane in alpha phase is F alpha, and multiplied with the mole fraction, which is basically x and b comma alpha, right? Or this is the value which we have. Sorry, we have to write down the mole fraction of hexane, right? So this is hexane comma alpha. If you put the values, so the value of F alpha is 0.8, and multiply it with fraction of hexane in alpha phase, right? That is 0.7, and this will give you 0.56. So the correct option is your option number A. So just to give you the formula, that if you have to calculate the fraction of hexane in alpha phase, that is also the ratio of moles of hexane in alpha phase divided by mole fraction of hexane in alpha phase. Okay, so basically the fraction can also be calculated like F alpha is also equal to the number of moles N alpha, that is number of moles of hexane in alpha phase. Okay, or I should write down it as N x comma alpha divided by the mole fraction of hexane in alpha phase. So that is x comma alpha. Okay, hex is for hexane. So if you take the ratio of number of moles of hexane in alpha phase divided by the number of mole fraction of hexane in alpha phase gives you the fraction of it. So the phase rule is generally used. So these are important formula. Okay, the most important formula is this one, these two ones, okay, regarding the fraction values, and then the important formula is basically to calculate the fraction and to calculate the number of moles from here. So this particular concept of your like from the phase diagram, this concept of lever rule has never been asked before this particular exam. It was asked in GATE exam, but in CSIR net this was a new thing which was asked, so you should know about it. You can also read about this lever rule in detail. I have discussed about all these things in my detailed classes where I am teaching physical chemistry in detail on our Gamma batch that is running right now on our app as well as on our website. So if you want, you can enroll yourself. All the classes are detailed classes in the form of video lectures. You can watch them, and it includes all the important topics of your physical chemistry. Apart from that, we also have launched a test series for GATE exam where the exam like interface is provided to you. Along with that, you have the detailed video solution for the question, so you can give a mock test, you can give a full length test, and then you can have a video solution of that. We also have topic wise mock test over there, for which we are not providing the video solution as of now, but you have questions in the form of like topic wise, so you can also do that. The best thing about this test series is all the questions are new, they are not repeated questions or they are not previous year's questions. So that is the one of the best thing about this particular test series. Along with these, we have also launched our ebooks for CSIR net as well as for GATE exam. These ebooks contains all the previous year's questions starting from CSIR net June 2011 to June 2024, as well as from GATE 2000 to GATE 2024. We have all the previous year's questions segregated topic wise, in which we have detailed solution of each and every concept. So you will get the solution of these questions which have been asked in the previous years in this particular ebook. You want, you can purchase it from the website. All the important links are there in the description of this video, so you can reach out to these important places and you can make your own purchase. So that's it from my side for this particular video, guys. Thank you so much for watching, and I will see you guys in the next one. Till then, have a great day. Bye bye, take care.